Hi, Year 10. Welcome back to COVID-19 Lockdown Science, Season 2. I'm sure you're all a bit disappointed that we have to go into lockdown again, but hopefully it's nice and short and we'll be back at school soon. What we are going to be doing during lockdown in science is looking at electricity. So we're going to be starting a new topic. Electricity and magnetism is a standard, NCEA standard that you'll be taking next year. So it's really important that you get a good basic knowledge of it this year to make it easy for you next year. The way we're going to be doing this is there'll be 2 lessons, video lessons like this a week. I think Monday and Wednesday I'll put them up. And on Friday we will have a online lesson, live Google Meet lesson, and I'll send out the email for that. And there'll also be some work on Education Perfect for you to do, which I'll put up soon. There's going to be 2 lessons like this on Monday and Wednesday. So what we're going to be looking at first is something called static electricity. This is the one which you're probably familiar with if you've played on a trampoline and got shocked by it. The first one that was discovered by people. However, it's not really as useful as AC or DC electricity, which we use to run, computers and stuff like that. This is the first one I'm going to look at. It's called static electricity, and the reason why it's called static means it's not moving. So something's going to have a charge, positive and negative, and something's going to have the opposite charge to it. So an example of static electricity, which you have probably seen before, is getting a balloon and rubbing it on your hair, and it gets charged and you can pick up paper usually. I'm not going to use my hair, I'm going to use this thing here. This is a possum skin blanket. Put it out of it. And this probably works even better. Possum fur is really, rabbit fur and stuff is really good at making a electrical charge. So we'll see what happens when I rub it on this. And here is my little bits of paper. See that? No. It's there. So as I rub this, it's getting a charge, and I hold it over the paper, and you see it flies up to it. And it only lasts for a little while, it's become a fair bit, and then it stops. So static electricity is only going to last for a little while until it gets discharged. So what's happening there? What is happening? So what happens is this. When I'm rubbing the balloon onto the blanket, electrons are getting lost from the balloon and they are sticking to the blanket. So no charge is being created or destroyed. What's happened are the charges are getting separated. Some of the electrons on the balloon are now going into the cloth, onto the blanket. So the balloon is getting a slight positive charge from losing electrons, and the blanket's going to get a positive charge. And this positive charge in the balloon is what's attracting little pieces of paper to it. It's not very strong, it can only pick up a few pieces of paper, but it is there. I'll do another example. I have another balloon behind me. You can see that. Here, I'm rubbing the balloon on the blanket again. And hopefully you can see, without touching it, I can move that balloon back and forth because I've made a positive charge on the balloon. Now, when you rub these two things together to make static electricity, one thing's going to gain electrons and one thing's going to lose electrons. And how do you know which is which? Well, some guy worked out the order of what things become negative charged, like Teflon, and what things become really positively charged, dry human skin, for example. So when you're on a trampoline, for example, this is probably when you've got shocked by static electricity, you have dry human skin, which is really likely to get a positive charge. And what that means is dry human skin is really likely to lose electrons. If it loses electrons, which are negative, it's going to get a positive charge. And if we go down to here to find out what trampolines are made from, they're usually made from something like polypropylene, which is a type of plastic. And as you can see, polypropylene is down here at the bottom, and it says most negative charges. So polypropylene is really likely to accept electrons, negative electrons. So when you're jumping on the trampoline, you're losing lots of electrons from your skin, and you are getting positively charged. And when you touch something that's grounded, like the metal on the edge of the trampoline, you're going to discharge all of those you're going to get a lot of electrons to balance your positive charge, and you're going to feel that as a shock. That's why these shocks happen when you're on a trampoline sometimes. Not that one yet, back to this one. So here's an example. Imagine this was my balloon, two balloons. There are only two types of charges, positive and negative, and that's if they gain electrons or lose electrons. Like charges repel, unlike charges attract. And in most objects, or in all objects, there are both positive and negative charges. This balloon here has both positive and negative charges. However, when I rub it on this, it's going to start losing a lot of its negative charges, and once it's got more than one of another, it becomes charged. So it's now negative. This can be done with a comb. If you try comb your hair and then hold it over paper, it will probably jump up as well. And it says here, materials that will hold electrons well, plastic, silk, and glass. So those are the things that you can rub in your hair and they'll become charged. And objects that lose electrons include metals, which can become positive. Here's an example of static electricity in the lab. We do have one of these in the lab, which if you ask nicely, we can use when we get back to school. It's called a Van de Graaff generator. And the way it works is like this. It's exactly the same as, let me go away. It's just the same as rubbing a comb through your hair or something, except this bit's your hair up here, the positive bit, and this is the comb here. And what's happening is this conveyor belt goes round and brushes past it goes past these brushes at the top and strips electrons away, and then it deposits them on this wand bit. So all the negative parts are going to go onto this wand, and the positive parts are going to go onto the top of the Van de Graaff generator. So this Van de Graaff generator has lost electrons from the top, so it's positively charged. And when this girl puts her hand on it, her hand's going to get positively charged as well, and her whole body gets positively charged. And what's making her hair stand up like that? You can think about that for a while. I'll tell you the answer in a second. Why does her hair stick up? Because she's positively charged. So let's see. So the reason why her hair sticks up is each bit of her hair gets positively charged, each single strand of her hair. And if you go back to this one here, it says like charges repel. If all of her hair is positively charged, then each bit of her hair wants to repel each other. And what's actually happening here is her hair's basically just trying to get away from each other. Her hair's trying to be as far apart from each other as it can. So it ends up standing up on end, frizzing out to avoid each other. That's what it says down here. The repelling electrons trying to get as far away from each other as possible cause the person's statically charged hair strands to repel each other and stick up. We have one of these at school. It doesn't work really, really well, but here's a video of a better one.
Van de Graaff. The Van de Graaff generator. If you're not real familiar with Van de Graaffs, they produce static electricity. They do a little bit something unusual to your appearance when you try them out. You can actually pull the top off of the Van de Graaff and look inside. What you would see is a roller at the top, one at the bottom, and a belt that sits on those two rollers. When we turn the motor on, that belt starts to spin really fast, and as it spins, there's a little metal cone that strips away electrons. So the Van de Graaff builds up a very strong positive charge. When we have a volunteer stand on our insulator, they put their hand on the Van de Graaff. It steals some of their electrons and makes them a very positive person. All of those positive charges build up in their hair, and they start to repel, similar to magnets.
It was very shocking and weird. I've never felt anything like it before, and you should come out to AMZ to try it.
This is Miss...
All right, leave it at that. So yeah, that's how a Van de Graaff generator works. We have a guy using it at school, but ours is definitely not half that good. So here's a form of static electricity which you will be familiar with, lightning. So during thunderstorms, the clouds, the really, really massive thunder clouds, can get positive and negative charges within them. So one cloud could have a positive bit at the top maybe and a negative charge at the bottom. The electrons, are more likely to go to some parts of the cloud than others. What happens is that the lightning will start developing a really big charge near the ground, and eventually when that charge gets strong enough, it can discharge as lightning and strike the ground, releasing a lot of energy. Extremely cool, but can be extremely damaging. So this is why people have lightning rods. Not so common in a normal house, but for big buildings they often have lightning rods. And basically what a lightning rod does is it attracts the lightning, which is good. So because it's the tallest object with a point on the end and made from metal, it is definitely going to attract the electricity. But the important thing about the lightning rod is that the metal bit goes down the roof and then into the ground. So the electricity doesn't get delivered straight into the house, except the electricity goes into the ground. So it just travels through the lightning rod rather than traveling through the house and catching it on fire. And here's another one, which is a danger of static electricity. Vehicles driving down motorways, driving down the road, the air can actually drag electrons off them. So if they lose electrons, the cars can start becoming positively charged. And you may notice that sometimes when you get out of the car and you touch it, it'll give you a bit of electric shock. Static electricity again. Usually that static electricity is not going to cause any damage because it's just a little shock. Only lasts a millisecond. But for trucks and stuff which are refueling or dropping off petrol, that little spark can ignite them and blow it up. So what they do is they attach this grounding peg here, this blue cable. Before they release any petrol, they'll connect this blue cable to a metal pole stuck into the ground, which is called a grounding peg, and that's going to discharge any any electrical static electricity quickly. And I do that before they start pumping the petrol out, so there's no chance of a ignition to start a fire. And this also sometimes happens in car racing. You might see when they go to fill up they have a pit stop and they're putting petrol in. If they're unlucky, sometimes that petrol can catch on fire. The car in the pit stop will catch on fire as well. All right, so we're going to leave it at that for static electricity. I am going to put up some work on Education Perfect. It is very small, and basically the reason it's there is just to see who is engaging and who is doing the work. The work itself won't take very long at all, but I am going to see who is doing it. So yeah, I'll upload that now, and I'll have another lesson ready for you on Wednesday, and then I will see you on Friday. Cool, thank you, and see you later.